Hi, good morning, Payam.
Good morning, Rose. How are you doing?
I'm doing well. Trying to get back to normal after the summer.
Yeah. Well, it's not quite over yet.
Back to school this week.
Oh, is it? Okay.
Yeah.
I don't have any kids, so I don't know when that's back to school starts.
Yeah, it feels early.
Mm-hmm.
Hey, Rob.
Hey, Rob.
Hey, how you guys doing?
Good. How are you?
Oh, how are
Yep.
you? Are you back in session?
Yeah, more or less. Okay, let me try and move a little bit. If I have my face block out the window in the background, it works better. How you feeling, Rose?
Oh, I'm recovered.
Good.
Yeah. It's just a few days.
How was the experience? Was it as bad as they say, or is it like a normal cold? Or
Yeah, it was like a cold. Like it was right after I was traveling. And I was sneezing a little bit. I have asthma that's been inactive for a really long time, and I did get kind of wheezy. But 2 days, I stayed in bed. I was a little bit achy, I guess, but it wasn't bad, thankfully.
Oh, that's good. Yeah, so I saw a study the other day that was looking at antibodies, and I think it was of the Omicron variant. And to remember the results, actually, my wife was reading them to me. 56% of those who've had the virus reported no symptoms. Didn't know they had it.
Yeah.
no. I can't tell if that's a good thing or that's a bad thing. I mean, on the one hand, it's good that so many people don't have any symptoms. On the other hand, they're going to be transmitting without knowing it, right?
It's everywhere, right?
Yeah.
I mean, even when you look at the people who've been sick and sick in a household where somebody else has just had it and tested positive, and then they test negative repeatedly, even though they're sick, right? There's just so much we don't know or don't understand.
Mm-hmm.
Yeah, this was back at the kind of the Christmas, New Year's period, but my wife and father-in-law both came down with it. And I spent 2 hours driving with them in a small car while they had it.
None of my kids tested positive, even though we were traveling together. We were sitting beside each other on an airplane. Like we were together the following few days, and none of them tested positive. So I don't know how to explain that.
I had the same experience. My partner had it for a whole week, and we kept testing every day, and she was always positive, and I was always negative. So whatever that means.
Yeah, I don't know.
I guess there's no David today, right?
Did he say he wasn't going to be here today?
No, I see that he's online. Let me ask him.
Oh, maybe he's having trouble logging in. Oh, here he is.
Oh, there he is. Hi, David.
Hi, David.
There. Hi, everyone.
How are you doing?
I being heard. How's it going?
All right.
What did you think of the conference?
Well, it started pretty poorly, but then it got better and better during the course of the day. I don't know how they picked the first two talks. They were like horrible. I couldn't understand any. I don't think anybody understood anything. but it was interesting for other reasons. I got to see some people I hadn't seen for a while, and I was sitting beside a guy who owned a plane, so that was also an interesting experience.
Wow. Okay. Yeah, I floated around. I didn't actually recognize anyone other than you, which I thought was pretty crazy. But literally, I didn't recognize anyone. So Chateau and I we went to this quantum gravity conference in Vancouver, here in town. They're starting up the Quantum Gravity Society, right?
Yeah. It's a pretty dubious enterprise that they've embarked on, but it's basically a bunch of people who have lots of money and who have some degree or interest in physics from their young days, and they don't know what to do with their money. So they say, why not create this institute and get all these Nobel Prize winners to join? And yeah, it was an interesting contrast between people who knew nothing about physics but brought the money, and people who were like Nobel Prize winners, and they were just trying to entertain all these rich folk by their stories.
Was
The
it
other
all the
thing,
Nobel Prize winners that were speaking, or were the people who were financing it speaking too?
the Nobel Prize winners.
Yeah, mostly the Nobel Prize winners.
So Roger Penrose was there in force at a sprightly 92. He was pretty amazing.
Wow.
And he was suggesting that there's evidence in the cosmic background radiation that previous big bangs are leaking into our universe, and that essentially the universe has no beginning and no end, which I thought was pretty cool.
Or is that universes?
Big bangs, if you like.
Universe,
Yeah. So basically he's saying that when a big bang goes off, the matter spreads out in a kind of a sphere. And if a previous big bang had gone off earlier and the spheres intersect, then essentially you have matter from both universes coexisting in the same space and time. And so the possibility of transmitting information over very, very long periods of time, it's possible. So I thought that was kind of cool. Had nothing to do with quantum gravity, but it was a cool idea. Yeah. And the other thing I would highly recommend, when are you coming up, Rose? You said you were coming to Vancouver.
I'm not going. After the coming back from Europe was a nightmare. COVID aside, just other stuff happened with my daughter, and it's just like, all right, I'm not traveling again for a while.
Yeah, we went to SIGGRAPH here in town week before last, I think it was, and of the 10,000, we now have a recorded, I think, 300 COVID cases at the conference. So it's still highly contagious and still out there. So.
Honestly, it's not even the COVID piece of it. It's just the difficulty in traveling because of that. Like the airports are just such a nightmare, and yeah, I've kind of gotten used to being at home and being comfortable.
Fair enough. The other thing I would highly recommend, Payam, is Tuesday evenings is pay by donation at the Vancouver Art Gallery, and they have a super duper really good exhibition on AI generated.
Oh yeah, I was aware of it. It's on my list, but I haven't gotten.
I went and it was extraordinary. Really,
nice.
Really.
Cool. AI generated what?
So, so you know what a GAN is, right, or an autoencoder.
Yeah.
So what you do is you train a GAN or an autoencoder, and then the little slice in the middle, which is the compact representation, you can basically fiddle with the parameters in that intermediate representation and generate counterfactual versions of an input. So you can essentially move around the latent space that's generated by the GAN and generate as yet unseen but visibly plausible outcomes. It's pretty cool, actually.
So it's generating artwork.
It's generating, yeah, it's essentially exploring the low dimensional counterfactual possibilities inherent within the latent space of the encoder. And I think that's really interesting because Payam mentioned quite a while ago that he was very interested in trying to find new stuff as opposed to just rediscovering priors. And I think that's a very interesting way of approaching it, which is you can interpolate between past experience, and what's in between is actually novel experience. So we might be able to discover novelty between by essentially saying the parameters, when I see this image, these are the parameters. When I see this image, these are the parameters. If I smoothly interpolate between them, what's halfway in between, it kind of generates very interesting imagery doing that.
These models are getting really, really good. Like the ones that work with language, like DALL-E 2, or now there's a free version, stable diffusion baseline, I think it's called. I think it's free, but you have to sort of sign up for the beta. But you can just ask it for a picture of anything, and it gives you really, really good pictures. If somebody asks for like blueberry spaghetti, and you let it like run for like a couple hours, and it was like a really like a spaghetti with blueberries like on top, and it's something that never existed, right? But it can like really coherently mix things up. And yeah, so I think it would probably really either help out artists or put them out of the job. I don't know which.
Yeah. So
So David, I got a question about that stuff.
yeah.
Can you use that sort of middle internal representation and build a classification or a clustering part of it? So
Yes. So essentially what you could do is you could present a series of images to it, and then take a snapshot of what the middle representation is for those images. And now you've got a new data set that you could cluster. So potentially, sure, yeah, you could cluster in the latent space. I don't know what that would mean, but you could certainly do it.
could you kind of do that in a in that same GAN type framework? But instead of having sort of a single output, you would have, say, one of two outputs. It's a classification.
What do you think, Diane? So you've got a latent representation of something. So there's a one-to-one correspondence between an input and the latent representation. Could you do statistics on the latent representation and project that back into?
Yeah, I mean, people do that, right? There's a thing called, I mean, this is pretty old. Like, I don't know what the new way of doing this is, but they call them conditional GANs, right? So a GAN basically consists of a generator and a discriminator. And the discriminator is basically what you're asking for. You can use it to classify things. And the generator generates the image. So they train it by making the generator so good that the discriminator don't know which is which. But then the discriminator is also trained to be able to tell. So they grow together. But at the end of the day, you could use one or the other. You don't have to use both. So like generators are obviously getting all the attention because you can generate new images or whatever, and it looks exciting. But the discriminator is basically a classifier, right? It could be a multi-class. You can pick it to be any kind of a classifier or even clustering branch, right? Does that answer your question? I don't know.
So here's an example. We take a bunch of x-rays of people with lung cancer, and we take a bunch of x-rays of people without lung cancer, and we transpose them into some latent space. And then we build a classifier in the latent space that can classify people with lung cancer versus not people with not lung cancer. And then we can feed in an image, and it can come up with a black box interpretation as to whether the patient has lung cancer or not by looking at the image, but by looking at the latent space of the GAN and seeing what the latent space, how close, we could essentially do a clustering style classification of the latent space and use it to do medical diagnosis. So,
But problem is, I think you always take a performance hit if you separate the two cases, right? If you separate the generation or putting things into the latent space from the discrimination or classification, if you separate it, you always take a hit. Because neural networks, the way they work is if you already know what you want, then you just train it and it would learn the representation or the latent space that's useful for your task that you had in mind to start with. But if you want to put everything in some universal latent space and then do something on top of it, you always take a performance hit and it might not work as well.
I'm suggesting that we use a traditional GAN and just train it to its logical conclusion and then use the discriminator as is, untouched. That's what they do in Murphy's. They actually use the generator from a GAN that was trained separately, and they don't actually touch the generator. They just essentially manipulate the latent space in order to control the output of the generator. But they don't actually retrain the generator. So that's what's going on in the Murphy's. You've heard of Murphy's, right? You take a few photographs of yourself and you can then change the viewpoint and the lighting. So that's what I've been studying. I've been reading about this whole transformation of computer graphics, and so that's my background, and the way in which machine learning is creeping into graphics is very unexpected and very interesting, and for me at least, not at all obvious what they're actually using the neural networks for. So I can give you some examples. One example is class-based GANs. So they train a GAN to generate chairs and only chairs. And so if you want a chair in your scene, or if you have an image of a chair that you want to be similar to, the GAN will generate visual representations of the chair in any orientation, from any light source. And then you can compose these objects like you would in a three-dimensional scene. You can put a chair there and scale it and position it. You can put a light in the scene. And essentially you can assemble photorealistic images of scenes without actually rendering triangles at all. You're actually just rendering these neural radiance fields and assembling them into pictures, which I think is extraordinary. That's basically a complete reinvention of that whole pipeline. And given that this actually works, what's interesting, I think, for our group would be to think about how we could take these techniques and apply them to other domains. So,
can we think about that with a concept of time on it? So what I'm thinking about is if you can train something to recognize a latent space at an earlier point in time.
So in the classification example, you would have a pre and a post, and you would train it on pre, and then you would train it on post, and then you would present a new prior, and it would have to classify whether it was from the past or the future, maybe?
Yeah, or then getting from that into prediction of, given your current latent space, these are the places that you can go with an element of causality added in.
So I was going somewhere slightly different. Where I was going was to try and something very similar. So you train a GAN, you take the generator with its latent space, you use the discriminator to generate an initial parameter set for something you care about. So you have some picture that you want to manipulate. So you project that picture into the latent space, and then you fiddle with the variables in the latent space to see what's nearby, right? And that to me is a kind of counterfactual analysis, right? So it's not causal, I don't think. I don't know enough about causal inference to tell you, but
I mean, it's causal for your model, right? Not for the world. So
Sure.
you would know what causes your model to give what, but it has nothing to do with the real world besides whatever thousands of data points you trained with it, right?
And the other really interesting thing to think about is, can we essentially design a latent space? So can we impose a latent representation on a model? Like if, let's take the laws of nature and physics equations. Can we somehow train a model to incorporate priors in the latent space like the laws of physics? That to me seems plausible. I don't know how you do it, but
Yeah, they do that. Yeah, it's a whole field. Like there's lots of papers coming, like probably started 5 years ago, 10 years ago.
okay.
Yeah, there are ways of putting in symmetries, putting in conservation of energy, momentum, all those things you can put in as different tweaks into the architecture.
Okay, so there are hybrid models which are a blend of black box and
yeah.
Do you know of anyone doing that in economics or in healthcare?
Well, I don't know, but I also don't know any economic laws that you would feel strongly enough that you would want to put in the architecture to limit other things, but Robert would know.
Yeah, supply and demand.
Well, supply and demand, or we could actually use it as a metric of fitness for different economic theories. So given that we apply the constraints of one economics theory to a training regime and the specification of a different one, which one has better predictive power?
Yeah, I like that approach.
Yeah. So, and there was one other idea. What was it? We were talking about it, Rob. I'm trying to dredge it up.
Well, let me go back to something I said. So suppose I got a Monet and a Van Gogh. Can I use the GAN to discriminate or predict which type of painting it would be?
Question for you, Tom.
Yeah, thank you. So I guess what is the GAN trained on?
You spoke of conditional GANs.
Yeah, so conditional GAN is basically the same as GAN, except that the discriminator, besides outputting whether this is real or fake, it would output a class. So it would output Monet versus Van Gogh as well. So you generate an image, and then the discriminator learns to basically say whether it's a Van Gogh or Monet, and you give it thousands of Van Gogh and Monet images, assuming they exist, and then it would learn. And then your discriminator basically is a classifier. So it's conditional on the label of the image.
Yeah, okay, so I mean, if I had a training data set of a bunch of Van Goghs and a bunch of Monets, then how would, any sense of how the GANs perform relative to?
So always worse, way worse. So
Wait,
it's always better. So it's always better to just train a classifier. If you have a bunch of images of Van Gogh and Monet and you want to tell the difference, it always makes sense to train a binary classifier. Forget about generative part, because the generators require a lot more data and the focus is on the generation. So in principle, the generative model is good, but in practice, you will always take a huge performance hit. So if you have a lot of data, it always makes sense to just train a simple classifier as opposed to a generator and then a classifier. But generator gives you a lot more, right? So if you want now to generate a new instance of a Van Gogh image that's never existed, you can't obviously do it with a classifier. But if you care only to know the difference between Van Gogh and Monet, it makes no sense to learn how to generate them. You can just tell the difference.
So that's where the sort of the neural representation part would be useful, is because you could start to tweak it and generate a new Van Gogh.
Exactly, yeah. I mean, presumably, if you had access to like infinite amount of imagery, if you learn a really, really, really good generator and you create a bunch of synthetic Van Gogh and Monet images and then train a classifier on it, I think you might theoretically expect to get better results, because maybe in your training data set of real Van Gogh and Monet images, some of them were missing and maybe you don't learn how to distinguish, but if you could generate like 100% accurately representation of the Monet and Van Gogh images, maybe you can then learn a better classifier. But it's sort of like a circular thing, right? You can't use the data you have to generate more data to then perform better. That's just doesn't work usually in practice.
I just posted a link to the first movie made with a GAN.
Oh yeah, I've seen that one. It's not very good.
It's not a very good movie, but it is a milestone nonetheless. So
On every vacation at a
but yeah, so the other question I have for your poems, I already keep throwing them at you. Are there GANs that work with time series? In other words, is there an LSTM variant of GANs that you know of?
I think so. I mean, I haven't worked with them, but you can generate time series with Gans. I haven't worked with them, but yeah, there's no difference. I mean, time is just, as far as these models are concerned, it's just the same as space. It's no difference, right?
Right.
Like I know.
Typed in LSTM GAN and it came up with conditional LSTM GANs. So there you go.
Yeah, you just stick all, it's like Lego pieces, right? You get like, you put the different things together, you get a paper, right? And people were, that's why you get thousands of papers in these machine learning things. You just look for a unique combination and you're in.
I don't really have a topic for this week, obviously. What were you guys discussing when I was away? Sorry, I missed a bunch of meetups, and I was just curious if you could recap some of the stuff that you covered while I was on holiday.
I don't have a coherent memory. I was just sort of, we were just chatting. I don't know if we chatted about anything specific.
Yeah, not enough dates on that short-term memory part. Yeah, we did talk about clustering that. Basically, I just got to learn a lot about PIAM. It's a really interesting guy.
Yeah, thanks.
Okay, so yeah, so I'm kind of going all in on this GAN latent space exploration thing. So I've been reading a bunch of different books, obviously. One of the things that Hume said that I find very interesting, this is going back to last week's, the problem of induction. He basically says it's impossible for us to imagine something new. All we can do is interpolate or reconstruct past experience. And what I like about the GANs is they actually fit in very nicely with that. When you use a large data set of priors to generate a latent space that you then move through, essentially the latent space almost guarantees that you're just blending past experiences. You're not creating anything truly novel in a kind of some sense, because all you're really doing is interpolating between past experiences. But these are certainly places that we've never visited before. So PIAM, you mentioned a while ago, which really triggered me, that you were trying to avoid just essentially regurgitating priors and generate something actually new. How would you approach that? Or are you thinking about this kind of idea of interpolating between past experiences or synthesizing them in some way to create new, novel? Okay.
Yeah, I think it goes back to the whole, your definition of novel, right? I think maybe what we are learning more is that what we think is novel is actually interpolating between a bunch of our past experiences as humans as well. Like, what is novel? Like, whatever any of us will come up with, you can probably decompose it into a bunch of different things from what we know, right?
Yes,
so in that sense,
Hume. That's not me, that's Hume.
Yeah, so in that sense, yeah, but I mean, you can call it not novel, or you can call it that is exactly the definition of novel, to combine in unique ways that you haven't done before past experiences. So maybe that is novelty. I don't know. I mean, what can you possibly expect? I mean, whatever you draw is going to be a bunch of shapes that are, I don't know, I guess you could do some abstract art of something, but that still is always decomposable to some shapes, right?
Right, but I mean, all literature is just a repackaging of the same words, right?
Yeah.
So can we create, let's not call it novel, but new? I mean, isn't that what emergence, I'm not talking about puffy emergence, I'm talking about the literature on emergence. Isn't that what they're trying to do? Is they're trying to essentially escape priors and actually go somewhere that isn't based on priors, or is that just literally impossible? I don't know.
But isn't that what we are already doing? Like, I don't know, like these Gans, like the blueberry spaghetti, I'm pretty sure that never existed as far as we knew, and you can create a picture of it. Isn't that novel? I don't know.
It's a counterfactual, certainly. Like it's an alternate possibility of something that could be, but it doesn't really.
But I mean, almost by definition, whatever you can imagine so that you can judge whether
Absolutely,
it's
yeah.
new or not. If you can judge whether it's new or not, you have to first imagine it. And if you imagine it, it must not be new because it must be a combination of stuff. I don't think there's any coherent definition of new for something that you can't possibly imagine, right? And I don't see how us imagining and the models like pumping out different interpolations of things are any different. If anything, they're better because we don't have like all those millions of pictures in our head when we are imagining things. You probably go by whatever you saw last couple of hours or whatever is in your mind at that time, right?
Mm-hmm. Very much so, yeah. So how are you going to approach this problem then? I mean, do you want to talk a little bit about what you're researching, or is that related or unrelated? I mean, how would you approach steering priors towards novelty?
Yeah, I mean, I never worked on the generation, like I never had the task of like wanting to generate new things, like which is in art or whatever. I don't know if you want to do it in architecture or something. What I tried to do a while ago that didn't work is what I just described to Rob. Like we had some data set, which wasn't small. It was maybe 10,000 pictures of ships. But some classes we didn't have enough examples of, and what we thought to do is generate a lot more ships, that is variations of all the ones that we have, and then retrain the model and do better. And that like failed spectacularly, it just didn't work. I mean, there's a lot of technical reasons for it failing, but I mean, first of all, like you mentioned, like interpolating in the latent space, it's not trivial to find the right directions, right? Like if you just interpolate, let's say you have 100-dimensional latent space and you just randomly start going in one direction, you're going to get nonsense, right? You're not going to get variations. You need to find the right directions that sort of correspond to things that feel natural to you. For example, in the ships, there was a direction that if you could walk, then you get the lengths of the ship go higher or get larger or smaller. There is one for the color, but then there's a billion other dimensions that if you just go across, you get nothing. You get like blobs of different colors and they have nothing to do with ships. So it's not at all like controllable. I mean, people have been working on, they call it like disentangled representations, where each dimension of your latent space corresponds to one thing that's independent of all the other things. So people, that's sort of one direction of research you can take it, right? And then sometimes those directions make sense for us, like it would be lengths or something simple. Sometimes it's something more complex, which maybe we don't have a name for it. So yeah, so people work on it. So it's like you can use things like mutual information, right? Just make sure that the information from one dimension of the latent space has nothing in common with every other dimension, right? So if you can minimize the correlation between the dimensions, then you can guarantee somewhat that each one is basically tweaking some other feature of your image.
Right, and so the way that we're approaching exactly this is to try and create a visual representation as you move through latent space of what's going on in the image. And if it's nonsense, then you can pick a different direction to travel. But the other thing that we're thinking about is visual differences, which is perhaps one of the dimensions is just super duper sensitive. And rather than moving in steps of 1, you want to be moving in steps of 0.0001. And the way that we're trying to do that is by comparing the so we take an image, which is generated. We then tweak the hyperparameter by a variety of different values, very small values to medium values, and we see how much of the image changes in terms of optical flow. Because there's a lot of psychological research that says if the amount of optical flow in the images is too high, it doesn't mean anything to us, right? It's just noise. But if we can slow down the journey through latent space so that the amount of information that's changing over a given time period is bounded, then we might be able to move through the latent space at a pace that we can continue to understand what's going on and gain intuitions for what those different dimensions actually mean. So that's one of the directions I'm very interested in exploring in VR, where you can essentially just fly around a latent space of a model, and it will generate counterfactuals for you as you move around. So in the architectural use case, you train again on a bunch of architectural models. You would then have a starting point. So you take a photograph of your own house, and then you could move around the latent space near your own house to nearby houses that are very similar to your house, but have a difference in some latent variable, and essentially gain a kind of system-wide insight into what possibilities are available to you given your starting point.
And that reminds me of another discussion we had in the context of clustering, right? The whole idea of similarity. I think that becomes very important, right? If you have two images, you want to know whether they're similar or not. The very naive things you do, you subtract every pixel from every other pixel, you sum it all up and you get a number. But obviously that doesn't work, right? Because if you just shift one image by a bunch of pixels, you're going to get like very different images. So then you need to basically do this distance function that you have similar in clustering in some other latent space. So then again, we run into the same issue we had there, like what is similar and what is different and in what way. And I guess as humans, we do it really well, but I don't know how to do it like in algorithmic sense, right? If somebody shows you a picture of a cathedral and a church, you have a sense that maybe they're somewhat similar, even if they're totally different colors, different places, different lighting conditions. But to have an algorithm say these are similar is really hard.
Absolutely. So can we integrate people into the loop is my question. Like, can we have people who are really good at this, fly around the latent space and essentially see if they can get from the church to the cathedral along some axis or series of axes to essentially try and create a hybrid between the two. Like, let's say that you take a selfie of yourself as you are now, and then you take a photograph of somebody else, and you use StyleGAN to essentially transfer the features of this other person onto yourself. That already works, right? So I can send you papers on this where I can actually bring up one. Basically, you can reproject all sorts of information from an external source onto yourself and essentially explore counterfactuals of what you could become, as it were. So, and that might give you a sense of how to navigate better, right? So you have these examples. So in the healthcare case, I keep coming back to the healthcare case. So, if you stop smoking now, what would it be like in 5 years? So then you could essentially take data from people who stop smoking and then map that onto yourself and get a sense for yourself what the differences might be. And you might be able to essentially create two different counterfactual versions of yourself to aid you in decision support.
Yeah, I saw something similar. It was about retirement investing. So they had two groups of students. One of them, they would age them into the retirement age. And then basically that would prime them to the summaries, that would prime them to start investing for the retirement once they saw themselves as an old person that they couldn't imagine before.
Did that work?
Exactly. Yeah.
Well, they say it worked. Like, I don't know if I believe it. You ask them, are you going to invest? They say yes after seeing the images.
next
You
10
know,
minutes.
that's the extent of the scientific method that's used in these studies. So I don't know.
Interesting.
Yeah, I mean, you could potentially think about the same type of thing with, I don't know, medication adherence or treatment alternatives.
Is that an inductive bias that's bad though? Like having all of these, you know, does that give you, so back in the day when we used to have video stores, or even in the current era when you go to Netflix or one of these giant video services, you end up drowning in choice and choosing nothing, right? Because there's so many different things that you could watch, and you don't have a strong bias towards any of them, that you basically just ignore all of these possibilities and do something else entirely, because the effort of trying to make a choice as to which one to watch and the pros and cons just isn't worth the effort.
Yeah, I think there's a name for it, right? They call it the paradox of choices by that psychologist Dan Gilbert. Like, he's written a bunch of papers and books about it. Basically, the more choices you have, the less happy you will be with the choice you make, regardless of how good it was, because you always think about all the things you could have had or you missed out on. So less choice is better.
Isn't this where the interventions come in, that you use the interventions that are available to try and constrain what you're going to do in the latent space? Like, we need some way to tie the intervention to a part of the latent space. It almost sets the direction that you travel in the latent space.
What do you mean by intervention in this context?
Well, for example, if we're talking about the X-ray case, David, when you explained it, first of all, you said in terms of like lung cancer, not lung cancer, that's not really very helpful, right? What's helpful is what are the treatments that were applied and then what happened after that. So there's the image itself, but then there's a bunch of metadata that gets associated with that. And we almost need it in time series form so that you can see the potential outcome given your current state if we generate you forward with the intervention, where you might potentially end up then. So there's both intervention and outcome associated with each of the images in the time series. There's a whole bunch of data that's outside of the image, I guess is what I'm trying to say.
Yeah, no, that's the key component. Yeah, that's a really interesting idea. That there's a clip, there's a data set called clips, which is an image sequence and text to go with it. And so you can use the image sequence to find out what the text would be, or you can use the text to find out what the image sequence would be.
Right.
Yeah, so
it's the blueberry spaghetti, right? So
yeah.
Like this intervention in image for, like this intervention applied on top of some word that you have to describe where you are today. This is the outcome of that.
So let's go touch. This paradox of choice, or whatever it was called, is very interesting, because we as humans have this negative outcome where if we're given too many choices, we end up choosing nothing and becoming unhappier. Is this something that we could push up into the machine learning realm and try and solve it there and produce a few choices that are very distinct, and then present a very finite list of choices to people that they can easily choose between, and it's very clear what that choice might be? And further, can we try and make those choices not just personal, but more broader, so societal or whatever? So even though you're making a personal choice and you're exploring your own counterfactual possibilities of your own future, can that somehow be correlated with the futures of others, so that we can have these systems kind of co-plan or co-explore counterfactuals that have many participants? Is that something?
It's a wonderful life.
Is that possible even? I don't know.
Well, the first one is just what recommender systems try to do, right? You have a billion choices, even on Netflix. They can't show you all the movies Netflix has available, right? So the recommenders, based on your whatever preferences, try to give you something that they think you might like. Well, how successful they are, I guess, is questionable, but that's what they're trying to do. But the second one, I think I'll be more worried for a dystopian future where who decides what choices should be offered to society, right? Whoever decides, they will have their own motivations, and yeah, so that's more tricky.
That's darker. Okay.
Yeah, I might interject a note of caution. I'm not familiar with this paradox of choice literature, but in the experimental psychology area, there's a lot of stuff that gets published, gets disseminated, and turns out not really to be true.
Right.
I mean, true in the sense of independent researchers can't replicate the results.
Yeah, we suffered from that at SIGGRAPH. We had, we tried to run an experiment there. We got a couple of hundred participants to go through the study, and the results were just gibberish. Like they were completely inconclusive. So, thank you, Pam. I'll check that out.
Yeah, but the experiment I saw, so there is, I guess, another step on top of the limiting the number of choices. Like apparently, if you make a commitment to a choice, so let's say you had 10 things to choose from and you picked one. So they had two groups of people. One group, they say, okay, you picked it, that's what you're stuck with. And maybe 6 months from then, they would ask them, okay, how do you feel about your choice? And then the other group, they had a few months to change their mind. They can go back and make another choice out of that 10 options. And then again, they would ask them, how do you feel about your choice? So the first group who had to make a commitment from the beginning and had no options to go back, they felt happier by a large margin compared to the other people who could choose and change their mind and go back and replace the painting. So yeah, I thought that was interesting too. Again, I don't know how reproducible that is, but.
That reminds me.
It says options have negative value, which is an interesting result in finance.
Yeah, so it was a Da Gama who burnt his ships when he arrived in America, so that to close off the option of leaving, so that everyone was committed to moving forward.
I mean, that's why it's called a paradox, right? Because you would think, like, if you just think rationally, more choice is better, you could just ignore it if you want to, and it should always be at least as good as having one choice, but apparently not, right? Because psychology comes into it. Like, it's not just about the logic.
Yeah, I have to look at that.
Interesting. So,
well, I got another question.
Yeah, go ahead.
So this deep embedded clustering paper that you shared, some time ago, is there code out there for doing that?
Yeah,
I have deck running.
Yeah, you had that. Okay.
Yeah, no, I have that code and it can run on my local machine. So did you have a new data set for it?
No, but I wanted to use that on that existing liquidity data set.
Right.
Which I still haven't shared with you yet, so we can do that.
So what's everyone reading? I'm just curious. Are you still chipping away at McGilchrist, Rose, or have you switched to something else?
I'm reading Dostoevsky right now. I've given up some technical stuff.
So that's a romantic, as in the philosophy, a romantic novel where it's talking about the human experience.
Yeah, I just finished Crime and Punishment and Notes from the Underground before that.
Crime and Punishment was a punishment in itself. I read it, I powered through it. It was a really hard read for me. I don't know.
I think he's very funny.
I haven't read any of those. So is it Dostoevsky?
Yeah, Joey, to drop it to you.
Sure. And what are you reading, Pam, these days?
I'm reading this book on information theory, which I kind of need for work, but I'm trying to get deeper into, I'm trying to basically apply information theory for logistics, which as far as I can tell hasn't been done, or I haven't done a thorough literature review, but it's like an interesting problem.
So this is in the bits and entropy, that kind of thing, right? Is that?
Yeah. So there is like all these Shannon's theories of whether once you have a message, it could be like an English text or anything else, there is an optimum encoding for it based on the frequencies of the letters or words in the language, so that you could minimize the amount of bits you need to encode it and then to transmit it to somebody else. So there's a lot of work on that. What I'm trying to do is, so we have a list of orders. Let's say we have a warehouse. We have a list of orders out of all the possible orders that could be. And then I want to find a way to put these items into the bins or into the warehouse so that a minimum number of bins satisfy all the orders. So I'm trying to translate that problem of transmitting language to a problem of fulfilling orders in a warehouse. Just trying to, which made me realize I don't really understand all these entropy stuff that is used. So it's a good case for, I don't know if it's actually, this is not the only way of doing this, but this is a way to do it in an interesting way. So I'm just trying to see. So basically, if you have an order list, what is the encoding, which is the warehouse locations of all the items that you need to use to transmit that order the fastest, meaning that basically you compress your order list into a way using the warehouse so that the transmission is as fast as possible. And transmission here means fulfillment of the order.
Are you using backprop or MCMC, or are you actually trying to solve this?
No, it's just information. It has nothing to do with neural networks or, yeah. So basically for every message, so I know the historical orders that has happened in the past year. So based on that, I know what is the entropy of every order list, which is, so the higher the entropy or the lower the entropy, the higher the entropy, the higher the uncertainty. So it means if the entropy is high, it means there's a lot of rare items are being ordered. So then you can quantify how rare your particular order list is and then try to match it with your warehouse. So it's all just from signal processing, information theory, has nothing to do with neural networks yet, unless I find a connection to make it useful, but yeah.
So when you say you can calculate the entropy against some canonical version, like is it some Euclidean distance from some?
No, entropy is defined as, so it's a sum over probability of each item times the log of that probability, right? And so if you have, let's say, 10,000 possible things you can order, and each one, you know how frequently it's been ordered in the last year, so you know the probability of those, and then you know which ones are ordered, you just sum that P log P over all the items you have, and that's your entropy.
Okay, I mean, I could argue that's a form of machine learning, but sure, yeah, okay. Fine.
No, there's no learning. It's a number you calculate. It's like this. It's fully deterministic. Has nothing to do. I mean, it is. You need to know the frequencies of the items. So in the English language, for example, there is an entropy of a message in an English language, right? There's a minimum entropy. Every language has its own, and actually you can calculate what is the redundancy in the English language, for example, right? Because you can get rid of a good chunk of, I think it's something like 50–60% of the letters in a message and still fully understand the message. So that's a quantification of redundancy in a message, which is needed so that the transmission is done more effectively. So if every letter was super critical for everyone to understand it, it would be a more compact representation, but it would be very susceptible to noise. And if one letter dropped, then you wouldn't understand it, right? So the whole game of information theory is to balance that redundancy with the minimum number of bits you need to transmit messages. So you can go and for every language calculate this redundancy, because we know, like, for example, the letter E is the most frequent used letter. Like, I don't know, the word "the" is the most frequently used. And you have like these tables that people have constructed of what is frequent and what is not. And you can use it to design, basically. The whole game of information theory is design encodings, which I guess, going back to our previous conversation, is representations, these latent spaces that in a most compact way represent everything you need to know.
I see. So it's about minimizing the dimensionality of the latent space.
Yeah, so that's one way, one metric, right? If you want to maximally compress your signal, right? But sometimes you don't want to maximally compress. You want to be maybe more conservative and be a little bit better with noise, right? So if it's something maximally compressed, then if you lose one bit of that compressed representation, you could lose your entire message, right?
So it's anticipating counterfactual possibilities in the calculation, so to minimize the impact of nearby counterfactuals occurring. Not, I see. Yeah.
I mean, it doesn't necessarily have to be counterfactual. It just could be any noise, right? Like in a warehouse, like maybe an item needs to be in one space only, but what if you run out of that? So then you put it in 5 so that in case you run out of one, there's still going to be some more. So you would waste a little bit more space, but you're more robust to fluctuations.
To overfitting on one particular outcome. Oh, very interesting. Okay. You think about that. Very cool.
There was, I don't know if you were there in the Penrose's, were you there for the Penrose's second talk?
I was there for the whole thing. Yeah.
Okay. So he said something. I'm actually going to send him a message. I don't know. So I don't know how to get. It's hard when they win something. It's really hard to find them. But he had a very interesting slide about entropy. I don't know if you saw that. So entropy, like when you start with like entropy in physics, is all sort of a measure of disorder, right? So if you go from some highest entropy state where all the like particles are everywhere, then you keep lowering the entropy, you get structures, right? You get things that are close together because those configurations are more rare, it means your entropy is going down. And entropy is always increasing. So usually you go from, so if you have two compartments separated by a door, if you lift the door, the thing mixes and you basically get into a more uniform state. So everything wants to go towards more uniformity in the universe. But then he said that when you add gravity, it's not the same. You actually get clumps. You go from something uniform to these clumps of matter, which are like galaxies, which look like they have lower entropy, but they actually have higher entropy. So that's the thing I really didn't understand. I wanted to ask him because, yeah, so it seems like if somebody just shows you a picture of something, you can't tell what the entropy is unless you know all the other stuff, which is sort of counterintuitive.
Yeah, no, I remember that section very well. So from what I recall of what he said, he was saying that all the other parameters in the entropy equation other than gravity are smooth in terms of scale. So this gets back to the renormalization group stuff you sent me a while ago, and I'm certainly not fluent in it. But part of the renormalization group stuff, as I understand it, is that some effects of scale invariance. So they happen at great scale and at a very small scale, so they kind of smooth across scale. And I think what Penrose's point was that gravity does not obey that. It is not smooth across scale. It's nonlinear. And because of that, it has this kind of inverse entropy effect. That's my understanding of what he said. But
yeah, if you find something to read about it somewhere else, let me know. I would like to get into it a little bit more detail beyond that one slide that he showed.
What did you think of his slide of quantum gravity, where he had the two kind of manifolds bifurcating? Did you understand that one?
Yeah, I mean, I'd seen it before. Like you're talking about the conformal mapping stuff he was talking about? Right
near the end, he was talking about, so let me explain to the others very briefly. So in quantum superposition, a particle can be in two places at the same time, right? So it can be here and here. However, if the particle has mass, in my understanding, very weak, then its mass here is different to its mass here because mass is dependent on distance, and because these two particles are actually physically at different points in space, they'll actually have different masses, and there'll be an energy difference between them because mass equals energy, right? So yeah, there was this really interesting device where they were creating these these superpositions of a particle in two positions, and they're putting that in a gravitational field. And I didn't really understand that stuff, but that looked really interesting.
Yeah, I didn't get the details so much, but I thought that was a clever idea. I mean, the whole point of, like, also the talk by Marcus, the Austrian guy, was really, really good.
Yeah, I think he was the top. I mean, Penrose was amazing, but Marcus was actually doing something useful.
It's one of the experimentalists who actually spoke. Yeah, the whole name of the game is, like, if you want to study quantum and gravity at the same time, you either need to go to like super large scale, like black holes, which is obviously really hard to do experiments on, or what these guys are trying to do is basically create as heavy as possible of a quantum system and then study it there. So there were two proposals. I think one was to, like, have these balls, like by Marcus, have these balls that are sort of putting gravitational forces on each other and trying to detect if there is anything quantum there. So basically, the name of the game is devise an experiment where if either gravity or relativity or quantum mechanics is wrong, you would see it in that experiment. And I think Penrose's idea was, because in quantum you have this superposition of the same thing can be in two places, then the mass would be affected by it. So then you should see a difference in gravity, because relativity doesn't have that, right? So one of them will be wrong.
Once again, I don't understand what the consequences of being right or wrong would be, but oh, we lost Rose. Sorry. She had to bail. It's time, I guess. So I guess my question then is, where do we want to go from here? I'm very interested in the Gans stuff. Is that of interest to you to go deeper into the Gans stuff, Payam, or is that not so interesting?
I mean, it's okay with me. I mean, you might want to look at the diffusion models now. As far as I can tell, they have superseded Gans. Like, they're in every way better, and they do exactly what you would want them to do. So that's sort of the next technology.
So what are those? I'm not familiar with them.
I think we mentioned it before. Like, basically in Gans, you start with random noise, like Gaussian noise, and you generate an image from it, and then the discriminator says it's wrong or right, and then you keep going, right? That's the Gans. The diffusion, you start with an actual image, and then you add noise to it in small amounts of noise in different steps. So in 100 steps, you add so much noise that you get to the fully, like, Gaussian noise. And then what the model does, you learn that mapping. Like, how do you the mapping between a slightly noiseless versus slightly noisier, and so on. You learn that mapping, and then if you play it backward, then you get a generated model.
So does that help solve the computational inefficiency of Gans that you spoke of earlier?
Not the computational inefficiency, I think, but it's a lot more stable. The Gans are very unstable. They're really hard to train. They're notoriously hard to train. So diffusion models are much more stable, and they seem to result in better quality images.
Do they have a latent space?
I mean, they both have latent spaces, right? It's just that you do it in a more controlled way, the diffusion model. So then I think you can almost be guaranteed to get something good, whereas GAN is like one shot, right? You go from noise to a full image, and you could go wrong in many different directions and never get to the full image, right? And you have to balance this discriminator with the generator very carefully. I mean, people have found all sorts of tricks of doing that now, so it's not as hard as it used to be. But I mean, DALL-E 2, the stable diffusions are all based on diffusion model. They don't use GANs anymore.
Oh, okay. I didn't know that, and I'll do some research on that. So maybe we'll make that the topic of next week.
Yeah, sounds good.
Cool. All right.
Thanks.
Yeah, so what book on information theory are you reading? I've only read anecdotal books.
So the textbook on it is by Cover and Thomas. Yeah, if you just go information theory, Cover and Thomas. So I'm using that as a reference, but I'm using this Penguin book, which is more friendly, by Pierce. Let me just find it. Yeah, it's called an Introduction to Information Theory by Pierce. So it's not a lot of equation, but I wanted to get the concepts. I feel like every time I think I understand entropy, I don't need a bunch of equations. I can figure those out later. I just need to understand what's going on. And I think this is really good. It's very short.
I got the Introduction to Information Theory. What's the other one? Sorry, I didn't get that.
So the other one So it's called Elements of Information Theory by Cover and Thomas. So that's the textbook for information theory. Yeah, so that one, if you take a course, this is probably what they're going to teach from.
Okay.
That's a much more rigorous. Yeah, so I'm trying to use this thing called Huffman coding, which I guess we
Yeah,
can
no,
talk
it
about
happened.
next
Yeah,
time.
yeah. I'm familiar with that one. Oh, interesting. Be interesting. I'm curious to try and map that into a machine learning frame and see if what's the difference between an information theoretic and a
I mean, there is
prior.
the IIT, right? The Integrated Information Theory folks, which is sort of trying to connect AI to information theory. It's like a whole theory. We can maybe have a look and see if that's something you guys find interesting. As far as I know, it's like kind of dubious. Not everybody sort of buys it.
What do you call it again?
I think it's called Integrated Information Theory, IIT. Yeah, there's a Wikipedia page. Basically, you get this phi, which is called it's this variable that you can never calculate. Basically, it's intractable, but it's supposed to explain everything. So it's a little bit dubious.
Okay, I'll have a look. Great. All right. Well, I'll chew on that and post something next week. Very good.
Yeah, you might like it. It's connected to consciousness and all sorts of things. So it might link a bunch of stuff we have talked about before.
Excellent. Very cool. Rob, I'll reach out to you. We'll meet early next week and continue the journey.
Good.
Excellent. All right, guys. Take care.
See you guys.
Appreciate it.
Cheers.
Thanks,
Bye.
everybody.
Bye.